There we go. Alrighty. So, so percentages, and I'm sure a lot of you have seen percentages before. You've done them in high school. It's probably fine, but this is just a little bit of a refresher. So percent means, it literally just means out of 100, right? It's like a Roman thing. I forget exactly the historicalness of it, but it's completely arbitrary. All right, so 100% is just one, right? It's one because it's equal to 100 and then 1 over 100, if that makes sense. Because out of 100, we can write as 1 over 100, right? So whenever you see a percent symbol, it's really just, it just means 1 over 100. So for instance, I could write 0.03. I could write this as 3%, right? Because this is the same as saying 3 times 1 over 100. And you can double check that with your calculator. If you, so what is it? 3 divided by 100, 0.03. All right. So the percent symbol just means the 1 over 100. So you're just dividing the percent symbol and putting it in, right? And so this is just back and forth. But then this one here, 50% of 40 is what?
20.
Yep, exactly. And so the way you could find that, because I mean, 50% is everyone can probably guess that that's half, right? But if you weren't sure, like if it was 17% or something bizarre, the other way you could do that is you could say 50% of 40, you could write that as 40 times 50%. And then as I said, the percent symbol just means 1 over 100. So this is the same as 40 times 50 over 100. And then you can plug that all in your calculator if you needed to, but you can also note that 50 over 100 is just 1/2, right? And so that's the same as 20 as well, right? And then this last little question, and again, this is just a little, we'll do these a little more formally later on, but 12 is blank percent of 48. So what percentage of 48 is 12? Right, so again, so this one you might have,
25.
yeah, it's 25, right? You might have just been able to guess that based on, you multiply 12 times 4, you get 48. A 4 is, 25% of 100, sort of. But anyway, the way you do that formally is you would do the following. So 25%. Maybe I'll start off with the other one. So I'll do 12 over 48, right? And that's equal to 1/4, right? But if you want it as a percent, you have to kind of force it to work, right? So this is equal to, so again, you can plug in your calculator. So 12 divided by 48 is 0.25, right? But if I want to put a percent there, I have to multiply it by 100. Because when I add a percent, I'm dividing it by 100, if that kind of makes sense, right? So to convert it to a percentage, I'm going to rewrite it as 25 or 0.25 times 100 divided by 100. And so this divided by 100 is just a percent symbol by definition, and 0.25 times 100 you can just do as 25. So overall, I get 25%. Right? So there's a few ways you can do it. But in general, if you want to find what percentage something is of something else, you divide the part by the whole. So I'll do part divided by whole times 100%. Right? So that's like the kind of loose definition. Right? And as I said, the reason you're multiplying it by 100 is because the percent symbol divides it by 100. And you don't really want to change anything. You just want to keep everything the same. But the percent symbol is just notation. Right? All right. So again, hopefully you've seen percents before. We're just going to use them as far as exponentials and growth is concerned right now. Later on, in Unit 2, we'll do a lot more with them. All right, any questions so far? All right, so the somewhere. Relative change. So there's going to be two kinds of change that we're going to talk about, and we've already talked about them in, I think, the first notes we did. Earlier, we talked about linear growth and exponential growth, and we said that linear growth was the same absolute increase or decrease every time, right? And that's going to be what this is. So an absolute change is the actual increase or decrease from a reference value. So it means it's the new value minus the reference value. And so by reference value here, you can think of it just as the old value. Right? It's just the initial value, and you're taking the difference. So for instance, a town's population goes from 123 people to 429 people. What's the absolute change going to be? Or how would we find it? So my absolute change, it's just going to be the new value minus the old value. So the new value is 429. And the old value is just 123. And that's it, right? So the absolute change is literally just how much it's changing. And in this case, it's over 1 year, right? But it doesn't necessarily have to be. So then again, you just finish it. 429, oops, 429 divided by 123, 306. Right? And in this case, it's people. So that's absolute change. So for instance, if you have a line, the absolute change on a line, every time you increase the x coordinate by 1 is just the slope, right? It's always the same. It's always the slope for a line. So when you think of absolute change being the same, you can just think of a line, all right? So that's the first thing. The second kind is called the relative change. And it's kind of silly, I have it right there, but relative change. And this is what's going to be important for us when we talk about exponential growth, right? So the relative change is the size of the absolute change compared to the reference value. So as far as the definition goes, you can think of it as absolute change over reference value, right? Alternatively, you can plug the definition of absolute change in, and you can write it as new value minus reference value. I'll just put reference val, come out of space, over reference value. Right? So it's just the absolute change over the reference value. So basically, it's how much did it grow compared to what it started as, all right? So we'll do an example in terms of stocks, right? So stock A goes from $5 to $10, and stock B goes from $20 to $4. What are the relative changes for the stocks? All right, so let's do stock A first. All right, so for stock A, what is my new value?
10.
And what's my old value?
5.
Yeah, exactly. So, so my relative change, again, you can just think of it as new minus old over old, right? Where old is the reference, right? They're just different names. The only reason I'm using reference value is because if you look up relative change in other books or like the internet, usually they'll call it the reference value and the initial value. So, or the reference value and the new value. I guess they're different names. There's nothing like, there's not a one name or whatever, but you'll often see reference. Anyway, so you just plug it all in. So I get 10 minus 5 over 5. And so what is that? That's just 5 over 5. So that's 1. As a percent, 1 is what?
100.
100, yep. 100%. And so again, whenever you're writing things as percents, make sure you put the percent symbol. Otherwise, it's not right. Because the percent symbol literally means divide this number by 100 to get the actual value. All right. So stock A grew by 100%. So they grew by 100%. So in this case, it means it doubled. To grow by 100% means that you grew by exactly what you were. You grew by 100% the entirety of your initial value. And so you're adding an initial value to an initial value, you get 2 of your initial values. So it just doubled essentially. Okay. Stock B now, let's look at that one. Okay. Same process. What is my new value gonna be?
4.
Yep, it's 4. My old?
20.
Exactly. And then all over the old, which is 20. And this one, we'll need a calculator, right? The numbers aren't as pretty. So 4 minus 20 divided by 20 is minus 0.8. Right? And then to convert that to a percent, just like stock A, you just multiply it by 100. So it's minus 80%. Right? So stock B lost 80% of its value.
That's quite a dive.
It's not great. So stock B, I'm gonna say decreased, or you can say decreased by or lost. Maybe I'll say decreased by 80%. Okay. And so the negative corresponds to the word decrease there. So you're losing value when it's negative. When it's positive, you're gaining value, all right? So again, the way you interpret this is your initial value was $20, right? And so to say you lost 80% means that if you took 20, let me move this in the light. If you took 20, oh, it's too bright there. There we go. $20 and took 80% of it, it's 16. So to say you decreased by 80% is to say you decreased by $16, which is exactly what we did because we went from 20 bucks to 4 bucks. All right. Any questions with that? All right. So this relative growth, as I said, is very important for our exponential functions. But let's look at a line before we finally get to exponential functions. So again, we're dealing with populations because it's the most natural thing to talk about as far as growth and decay is concerned right now. But suppose the population of a town is given by the linear function p of t here. So our initial value is 1,000 people, initial population, and then this is our slope. Right? And so what that slope is telling us is that we're growing by 250 people every year. Growing by 250 people a year. And that gets back into the units of the slope, right? People is what our function has for units, and years is what our variable t has for units. So it's the variable y, or a unit, the unit of y or the unit of x. So people over years. Let's fill the chart. Alrighty. So in year 0, what's our population? So the year here is just t, right? How many people in 0 years? If I plug in t equals 0 into
1,000.
1,000. Yep. Oops. So I get 1,000, and so I can't do the relative change here because there was no That's it. We don't know what the population was before that, and so it doesn't make any sense. You need an old value, right? So we don't have any new value, so we can't do it for the first year. Anyway, what is the population in the next year going to be? In year 1.
1,250.
Yep. All right. And now we can compute a relative change because we have a new value, we have an old value. So let's do it. So I'll try to fit in this box. Hopefully it's not too tiny. But my new value is the population in this year 1. So I have 1250 over minus the old value, so minus 1,000, all over the old value, 1,000. And let's see what that is. So can you see, let's do that there. 1250 minus 1,000. Oops, 1250 minus 1,000, the 0, divided by 1,000. So it's 0.25. So I'll put that in 0.25. And then of course, if you want it as a percent, what do I do to it?
Move the decimal 2 places to the right.
Yeah, that works too. You move decimal 2 places to the right, so it's 25%. The other way of doing it, it's multiplying by 100, but it's exactly the same. Right, cool. All right, let's do the next year. What is my population in year 2?
1,500.
Yep. All right, and let's do the reference value or the relative change now. So it's the new one, 1,500, minus the old, 1,250, over the old, 1,250. And so you'll note that the old and the new values are changing, right? It's shifting. So the new value is always the current year population, and the old is always the year preceding it. So you're gonna get different numbers. So I'll do the same thing, 1,500 minus 1,250 divided by 1,250. And this time I get 0.2. And so as a percent, that's what?
2%.
Careful. So
20%.
20%, yeah, you're multiplying it by 100. So if you do like that, you get 20. But if you're doing it by moving the decimal point to the right 2 places, you move it to the right once, and then again. And when you move it again, you kind of have like a phantom 0. And that's why it's 20 and not 2, right? All right, the next one, we have population, what is it, 1,750?
1750, yeah.
Yep, and we'll do it again. And let's see, so 1,750 minus 1,500 over 1,500. Let's see. So 1,750 minus 1,500 divided by 1,500. And I'll just round it to 0.17. And as a percent, multiplied by 100, that's about 17%. Right? So you can see a pattern emerging, right? As I go and make my table, the relative change is getting smaller and smaller. And we'll just do one more because I think you'll be able to see it. So the next one's what, 2,000? And so I'll do 2,000 minus 1,750 over 1,750. Right? And let's see what that one is just to finish this off. So 2,000 minus 1,750 divided by 1,750. So about 14 or 0.14. Right? And then again, you can finish this off if you want. But the whole point is that for a line, the relative change decreases as you go along. In this case, because your line is increasing. So maybe I'll put that at the bottom or on the side. So as x increases, or t here, sorry, t increases, the relative change decreases. Right? And so that's the thing about a line, is that relatively the function is going to be increasing or decreasing at a smaller and smaller rate. And it won't ever get to 0, right? So you'll notice in this chart, we started off at 25, we dropped 5, we dropped 3, we dropped 3. What's going to happen is it's just going to keep getting smaller and smaller. And it's going to approach 0. Like if you did 1,000,000 entries in this table, you'd make it really small, but it'll still be growing at some very tiny rate, right? but that's the one thing. So any questions here? It's kind of cool, actually, right? Let's look at another example. Basically the same thing, but now our town is growing by 5% each year. So now what's going to happen is that our relative change is going to be fixed at 5%. Every year, the town's population grows by 5%, all right? Which is, again, in contrast to this case here, because here the relative change varied, but my absolute change was always 250. So this is my absolute change is always 250. So in this line example, the absolute change is fixed at 250. The relative change is allowed to vary. In this next example we're going to do, the relative change is going to be fixed at 5, but the absolute change is going to be allowed to vary, right? So it's the exact opposite. And this is going to be an example of exponential growth. Right? So let's just do the table though and kind of play around with it. So maybe I'm gonna make this simpler. I don't know why I put these numbers in. I'm just make it 10,000 flat. All right, it doesn't matter, but I don't know why I put 1042. So in year 0, what's our population?
10,000.
Yep, 10,000. And just like in the previous chart, we can't really talk about relative growth and we don't have any population growth because we don't know what it was before. All right, so now, how do we compute the population growth in year 1? Right, so what's it growing by?
Percent.
Yep, it grows by 5%, right? So if we want to figure out how much it's growing in the first year, we just have to take 5% of whatever the population was. So the population was 10,000. So to figure out the population growth, we take 5% of 10,000. So it's 10,000. And whenever you take a percent of something, all that means is you're multiplying it by the percent, by the way. I don't know if I mentioned that. So when I say take 5% of 10,000, I'm just saying take 5% and multiply it by 10,000. So 10,000 times 5%. And again, the percent just means over 100. So when I plug it in my calculator, see if I can get a good view here. There we go. I do 10,000 times 5 divided by 100. So it's 500.
Can't you just do 10,000 times 0.5?
0.05. Yeah. So you can do 10,000 times 0.05. So that's, so to go the other way, so to go from a decimal to a percent, you're moving the decimal place to the right to go to a percent to a decimal, you move the place to the left to. So maybe I'll put it up here, but 5%. So my decimal place is like right after the 5. So I go over 1 and then over 2.
Oh, I see what I did. I did 1,000 instead of 10,000.
Oh, okay. Gotcha. Right. And then, so this is the amount that our population grew in that first year. So to get the population that year, I take 10,000 and add 500. So I guess I should have flopped these two columns, but it's okay. So I do 10,000 plus 500. And so I just get 10,500. Does that make sense so far? So the population in year 0 was 10,000. We took 5% of 10,000 and added that on to get the population in year 1. And what's the relative change going to be?
500?
Huh?
500?
So that's the absolute change, yeah. So may I'll put that over here. I should have made a column for that. Absolute change. So the absolute change is just going to be, so this is NA. So this is just going to be 500. Well, I guess the absolute change will be the population. That's okay. But the relative change is going to be the new minus the old over the old. So it's going to be 10,500 minus 10,000 over 10,000. And you don't even really need to compute it if you think about it, but we'll do it. Let's see if you can see that. There we go. So it's 10,000 5,500 minus 10,000, and then divide it by 10,000. So it's 0.05 or 5%. Sorry, I'm kind of running out of space there. But as I said, the relative change for all of these columns or all of these rows will be 5%. So without doing any more work, you could write 5% down this entire column, because that's how we're constructing the population. Every year it's growing by 5%. So if you go and compute the relative change, in every case it should be 5%. All right, let's try the next one. So the population in year 1 is 10,500. Again, to find the population growth, I take 5% of the population the year before and add it on. So I do 10,500 times 5%. And just like we did a minute ago, let me move this up a little. There we go. So I do 10,500. And then again, you can move the decimal place over, or I'll just do times 0.05. It's 525. So in the second year, I gained 525 people. And so the absolute change is 525. The relative change, as I mentioned, will always be 5%. And the new population, I just add 525 back on to the population year before. So it's 11,025. Right, so is this making some sense so far? Let's keep going. So the next year, so I do the previous year's population, 11,025, and then I take 5%. So just like I just did, so it's going to be 11,025 times 0.05. So this year it grows by a fractional amount of person. It doesn't really matter. I'll just round down. So it grows by 551 people. Right. So again, my absolute change, my population absolutely is growing by 551 this year. But relative to the population, it's only growing by 5%. As I said, just by the construction. And then to get the actual population, we add this number, the population growth, to the population of the previous year. So 11,025 plus 551. And again, I'm rounding down. So if you do the relative change, it'll be slightly off, but it's okay. So it's going to be 11,000 something, 11,576. Right. Any questions so far?
No.
No, we're all good? All right, we'll just do one more. We'll go to 4, just like the previous example. All right. And so again, so 11,000, we take the population from the previous year. Oops, 6, sorry about that. And take 5% of it and add it back on. So this will be 11,576 times 0.05 again. So I'll round this one up. So 579. And then again, you add that back on to the population of the previous year. So 11,576 plus 579. So it's about 12,000 something, 12,155. Right. And again, the relative change will always be 5. And the absolute change is just how many people you added. So in this case, it's 579. All right, and again, you can complete this chart if you like. So let's compare. So the important part is that we compare the chart that we just won and the one we just did. So as I said, the relative change here is fixed, but the absolute change is going up. So we're adding more and more people every year. Compared to this chart, we're adding the same amount of people every year, but the relative change is going down because the population as a whole is getting bigger. And so the amount, if it's growing by 250 every year, but the population is now 2,000, 250 is a smaller percentage of 2,000 than it was initially. Right. Questions? All right, so now the important part. I guess this is all important, but can you find a formula for the population in terms of the year T? So let's look at what we did to compute the population and see if we can figure out a formula. So first year, it was 10,000. So nothing really exciting there. But we'll write 10,000. There. Second year. So what did we do? We computed 5%, and then we added it back on, right? So maybe I'll do it on a separate sheet of paper because I want more space. So we have 10,000, and this is t equals 0. T equals 1, we have 10,000, but then we added on 5% of it, right? So it's plus 10,000 times 5%. All right. Alternatively, I can write that as 10,000 plus 10,000 times 0.05. All right, and now how can I simplify this? What can I do? Any ideas on how I can simplify this expression?
Combine the two 10,000s.
Exactly, I can combine the 10,000s, right? So it's a little algebra, but what you want to do is you want to factor out the 10,000. So I can write 10,000 parenthesis, and so I have a 10,000 here, right? So if I'm factoring the 10,000 out, I have one of them here, and then plus, and I have 0.05 of them here. All right, so if I simplify it even further by combining these together, it's really just 10,000 times 1.05. All right, questions with that? All right, so now let's do t equals 2. And so again, we're just kind of playing around with how we found it, try to find a formula. And this is kind of our starting point. It's like a guessing game at this point. So for t equals 2, we took the 10,500 and we added on 5% of it. So just, I'm gonna be a little hand wavy, but so what we did was we took 10,500 and we added on 5% of it. All right, and again, I wrote 5% as 0.05. So this is 10,500 plus 10,500 times 0.05. All right, so now it's gonna look a little weird, but this population here, right, this is equal to 10,500. So I can substitute this expression in for 10,500. As I said, some of you might just have your eyes rolling back in your head. But I think it's kind of cool. We'll just stop after this one and I'll give you the formula. But I think it's kind of neat just to see where it comes from maybe once in your life. 10,000, 1.05 times 0.05. All right. And now we factor out the 10,000 times 1.05 from both as well. So I get 10,000, 1.05. And I'm sorry, again, just like before, I have one copy of them here, and I have 0.05 copies of them there. All right, and you combine it again, and you get exactly, so you get 10,000, 1.05 times 1.05, and that's just 1.05 squared. And so I hope you're all still alive. But this is kind of a hint at our formula, right? So when t equals 0, we just have this, 10,000. When t equals 1, we have 10,000 times 1.05, and you get one of those. And then when t equals 2, you get two of those. And so you could guess that the population at year t is, so 10,000, 1.05 to the t. And that turns out to be the right answer. So instead of doing this table over and over and over again, so like for instance, if I asked you to do the population in 20 years, you'd have to do 20 of these tables or 20 of these rows on this table. And it could take you a few minutes. But with this formula, you just plug t equals 20 in, and that will give you the population in 20 years. All right? And so this is an example of an exponential function. This is an exponential function. And so that's exactly where these next notes start off. So any questions about all this? Again, If you didn't like this table thing, just kind of keep in mind the idea of absolute and relative change. You don't need to worry so much about this, but I just wanted to show you kind of where exponential this equation comes from, because otherwise it's more of like I'm just throwing it at you, and I don't really like throwing equations at people. All right, anything? Awesome. So let's get into those notes that we ended at Tuesday. So these are back. This is the second half of notes 3, right? Sorry to kind of jump around. All right. So let's see. Let's just go to this page first. So an exponential function. So this is page 6, by the way. An exponential function is any function of the form, and usually it's a, b, and I don't have a variable here. Oh, I do x. There you go. A, b to the x. And so b is positive and not equal to 1. And I should note that a is any number. So for example, you could have like 3 times 2 to the x, or 0.1 times 1/2 to the x, things like that, right? Anything really goes. The reason you don't want b to be 1 is if b is equal to 1, then there's no function, it's just a constant, right? Because then if b is 1, this is 1 to the x, which is always 1. So it basically vanishes and you just have f of x equals a, right? So that's why we exclude that case. And if b is negative, if b is negative, then weird things happen. Because think about it, like suppose your b is -2, then for certain values you'll be positive, for certain values you'll be negative, and you kind of jump all over the place, and it gets really messy, and we don't want to talk about it. So we kind of make ourselves restricted to the nice cases. A can be anything, right? The domain of an exponential function. Is there anything I can't plug in here? So like, are there any values of x that I couldn't plug into that? What is, so let me see.
Negative value.
Oh, that's good though. Let's look at what happens when you plug in a negative. So I'll do it off of the side of paper here. So f of x equals a b to the x. And let me plug in some actual numbers so it's a little more concrete. So how about f of x? I'll just do 3 to the x. So this is with a equals 1, b equals 3. All right. So if I plug in a negative, so f of -1, say, so it's 3 to the -1. What is 3 to the -1? You might have to go back and recall some exponential properties from like high school. But if you don't remember, whenever you have a negative exponent, it just flips it into the denominator or the bottom. So this, by definition, is just 1/3. So it is well defined if I plug in a negative. For another example, if I do f of -2, it's 3 to the -2. And so it, strictly speaking, when the negative is in the exponent, it flips, it puts this down in the denominator and makes whatever the exponent was positive. So for instance, this one, 3 to the -1, is really 1/3 to the 1. But 3 to the 1, of course, is just 3. So it's really just 1/3, as I said. But here now, when it's -2, I put it in the denominator. I make the exponent positive. And so now what is this? What is 1/3 squared going to be? Anyone? Hello.
1/9.
1/9. So quiet today. All right, 1/9. Let's try another one. What about f of 0? What's f of 0 going to be?
1.
Exactly. It's 1. So 3 to the 0. Anything to the 0 is 1. And then, of course, the positive ones are acceptable as well. So f of, say, 4 is 3 to the 4. And what is that? 3 times 81? So remember, so 3 to the 4 exponents, you're multiplying that many copies of the number. So it's going to be 3 times 3 times 3 times 3. So it's 9 times 9, which is 81. All right. And then if you're really thinking about it, you might be like, well, what if it's a fraction? What is a fraction going to be? So what is f of 1/2, right? So maybe I'll plug it in. I get 3 to the 1/2. Does anyone know what 3 to the 1/2 stands for?
3.5.
So that
Or,
that would be 3 plus 1/2.
oh yeah.
Yeah, so it's kind of funky. So as I said, for 3 to the 4, as I said, you're multiplying it by itself 4 times. And that kind of makes sense intuitively. But for 3 to the 1/2, you can't multiply something by itself a half of a time. So any ideas what it means? If you take more math classes, it will be useful for you. Like if you take pre-calc, you use this a lot. But it means the square root. So fractional exponents stand for roots. So if I did f of 1/3, it would be 3 to the 1/3, and that would be the third root of 3. Not really, we won't really use these too much in this class, but it's just something to, you know, remember, keep it back of your head a little bit. You might come across it if you do take more math classes, especially like a calc class. But anyway, the point is that it's well defined everywhere. You can plug in any x value into this function and it's okay. So going back to my notes, the domain of an exponential is all real numbers. And so again, I'm stressing that notation a little bit, or that definition. Domain, again, just means the numbers we can plug in into a function. Right, so the domain of a function, if you forgot, is all the numbers you can plug into the function and for it to make sense. So for instance, the square root of -1, it's not defined for us. We don't talk about imaginary numbers. So we would say the domain of the square root function is everything that's positive. Right? Oh, and I don't know if I mentioned real numbers. Real numbers are just natural numbers, fractions, decimals, everything negative, positive, in between. Right? So basically, it just means everything possible. All right. So questions there? So this is the definition. This is what we're talking about when we talk about an exponential function. As I said, this we just talked about is an exponential. My a is 10,000, my b is 1.05. All right. Now the graphs of these are kind of interesting, and they have two shapes, right? So they either look like an exponential growth, like a really fast curve going up, or they look like exponential decay, which is exactly the opposite. So for growth, so how do I say? So so either, I'll just do it this for now. Either growth. So in that case, it looks like that, right? It's like going up. Or decay. So in decay, it's doing exactly the opposite. Right? And you can see why it's called growth or decay, right? This one is increasing, this one is decay. It's decreasing, it's going down. Now, if you've seen like charts of like coronavirus cases, oftentimes parts of them anyway will look like exponential growth because viruses, just like populations, generally grow exponentially because you have one people contacting multiple people, and each of those little people are contacting multiple people, and it's just like this big tree that grows out really fast, and that it's described by exponential growth. And the graph looks like this often, unless measures are taken to prevent it, like social distancing and masks, and there's natural things too that happen. So anyway, decay, you'll often see if you take like a chemistry course, you'll talk about exponential decay with like radioactive materials and things like that exhibit this process as they decay with their half-life. And we'll talk about this probably next week. Right? So questions about anything so far? Graphs. Again, you really just want to know the general shape. You want to know kind of what the two options are for exponential growth, what they kind of look like vaguely, and how they differ. They're not lines, right? They're not straight. They have this kind of curve to them in either case. Right. Cool. Let's see. All right. I just want to define some more things, then we'll do some examples. All right. So if R is the decay or growth rate, then the exponential function can also be written in the form. So I'm going to write it as, actually, I'm going to scribble this out. I'm going to put P of t, and this is the one we'll use more often than not. So this one, maybe put a star next to, is equal to P naught 1 plus little r to the t. All right, so again, star. This is when we talk about exponential functions and growth or decay, this is really our go-to. Right? So if r is positive, P of t is exponential growth. If r is negative, P of t is exponential decay. Right? So let's go back to our handy dandy example we did just a little bit ago. Let's see if I can fit both of these on the screen. There we go. So this is my general form, right? My P naught, oh, I should label these. This is P naught's my initial population. I'll say initial value / population. Because again, this exponential decay or growth formula can model like a wide variety of things. It doesn't have to just be populations. It can be radioactive, like carbon-14 decay. It can be like a fruit fly population. That's population, I guess. It can be a lot of things, coronavirus cases. So, but oftentimes, it's population. But this in general is the initial value. Whatever you're modeling, this is what it starts at. And then R is the decay or growth rate. And so again, to compare it to this case, my P naught is 10,000. And my little r is 0.05. Right? So your little r is exactly how much it's growing or decaying each year. So in this case, it was 0.05 or 5%. But in other cases, it can be anything. So this formula makes it really easy for you to model exponential growth or decay, just because this is often how the information is presented, right? So for example, I guess we'll do this one. I got a couple more on the other page. So let r equals 1. Explain what the function 1 plus r of t is modeling. Right, so let's just plug in r equals 1. So f of t equals 1 plus 1 to the t. And so this is 2 to the t. But we can interpret it, right? So if my r is 1, then it's 100%, right? So all it means is that whatever this is modeling, I don't give you any details. So it could be a population of like bacteria, or it could be a magic coin. All it's saying is that whatever this is modeling is doubling. So if r equals 1, the function models something that is doubling. And that is, may I say, growing by 100% each unit of time. Right? So that's what, when r equals 1, all you're saying is that it's growing by 100%, or 1, every t increases. So in the case that t is years, every year it's growing by 100%, or it's doubling every year. All right? All right. Any questions about that? So when r is 1, it's doubling. It's growing by 100%. All right. So let's look at those initial examples that I had here. So this is on the first page. Sorry, again, I'm not very ordered very well, but so as the population of ants grows each year by 50%, how many ants will you have in 6 years? And I should give you, if the initial population is, I don't know, how many ants do you want? 400. So you could make a table like we did way back at the beginning of class. but that's not very efficient, as I said. So let's just plug this into the equation we had and see what happens. So P of t, again, this is the really important equation. So if you've zoned out the entire class, the thing to keep in mind is this equation. So it's P naught 1 plus R to the t. And so my P naught is the initial population. So it's 400. And then 1 plus little r. And little r is the growth or decay rate. So that's going to be 50%. And you have to be careful when you plug it in because you can't just put 50%. You have to convert it to a decimal because the computer, your calculator won't understand what 50% is. You know what I mean? So it has to be in a form it understands. So it's going to be, maybe I'll write it out as 50. I'll put it as 50% initially, and then I'll simplify it. How about that? So this is 400, 1 plus, so it's going to be 50 times 1 over 100 to the t. All right, and then you might just know what that's 0.5, right? So you can check, but so it's, let me put this here, 50 divided by 100, 0.5, like you said. So this is really just 400, 1 plus 0.5 to the t. More simply, 400, 1.5 to the t. All right, so that's our model for these ants. If we want it in 6 years, what do we do?
Would you put the 6 where the t is?
Exactly, yeah, you plug in t equals 6 because t represents time in this equation. So maybe, whatever, I'll put it up here maybe. So at 6 years, we plug in t equals 6. So P of 6 equals 400, 1.5 to the 6. And strictly speaking, that is an answer, but you want to, you want to probably plug it in. So 400, and be careful when you're plugging this in your calculator. So if you have a scientific calculator, you have to be kind of more careful than if you have one of these graphing. But if you have a graphing, you just do time, so it's going to be 1.5. And I don't think you need the parentheses. I like to put parentheses whenever I want. You can't have too many parentheses. And then caret to the 6. So it's actually quite large. So it's 4, 5, 5, and I'll round down 6 ants. All right. So again, on this kind of calculator, it's easy. If you have a scientific, what I like to do is I like to put, let's see, I haven't used one in a while actually, but I don't know if you can see it. Where is it? There's going to be like a little exponential key somewhere. Oh, here it is. So I'm going to do 1.5, and then there's this little caret right there. You caret to the 6. I'll compute that first, and then I'll multiply the 400. And you get the same thing, all right? So if you have a little scientific one, just make sure you're using it carefully. You also can use your phone calculator.